So this video is going to take a look at parametric functions. Parametric functions are kind of the typical functions we might use in a physics class when we start talking about one-dimensional or even two-dimensional kinematics, which just means we're looking at the study of motion. The reason we look at parametric equations is that we're not going old school and relating y as some function of x. We really want to be able to relate both of those coordinates as some function of a parameter t. And so when you think of parametric functions, you usually start talking about time. So let's look at a nice easy case of just kind of linear motion. Let's start at a coordinate point, 7, 2, and this is on the y-axis. Okay, and then let's go to some future point over here, and we'll say that's 11, 10. Okay, we're talking about the motion of that. Okay, so let's say this is at t equals to 0. We're at this location, and let's say here this took us 4 seconds to get there, and we walked that direction. And so look how many things I can describe now. Now I could come up with an equation, y is some function of x, to describe this. Great, we could even do that if we want to, but that doesn't really have much power. That just gives me all these coordinate points. I want to know, I started here, I walked this direction, I ended up there, and how fast did I even walk? And not only how fast was I walking, but how fast was I moving horizontally and how fast I was moving vertically. I'm going to be able to describe all of those things as a function of time. Okay, so what we want to do here is we want to get x as a function of time and y as a function of time. Okay, so let's think about this. This is nice linear motion. So if you think about in terms of your x, we started at 7. And then what did we do? Well, we went from 7 to 11. So it means we went 4 meters to the right, and we did that in 4 seconds. Well, if we did that in 4 seconds, that means we were traveling 1 meter per second horizontally. So I'm just going to put a plus 1t. You see how when I plug in t equals to 0, I get 7, and I put t equals into 4, I get 11, and it matches. And really what I did there, I controlled my starting position, and I controlled my horizontal velocity, and I made it 1. Now let's look vertically. Vertically, I want to start at 2, and I go from 2 to 10. So I go 8 meters up in 4 seconds. 8 meters in 4 seconds is 2 meters per second vertically, so plus 2t. You see how I have 4 degrees of freedom right there? I got to control horizontal and vertical starting position, horizontal velocity, and vertical velocity. And again, I know in a pre-calc class you might not talk about this, but we do know how to take derivatives, so we can look at dx dt. That's the derivative of x with respect to time. That's just 1. But again, that's just our horizontal velocity. What's dy dt? Well, dy dt is just equal to 2. In a physics classroom, we wouldn't say dx dt and dy dt. We would label this thing just as vx, and we will label this as vy, because that's what they are. It's your horizontal velocity and your vertical velocity, and they're constant. Well, yeah, they're constant in this linear case, because we're kind of starting here and we're running towards this point. Now, future things, well, they'll be functions of time as well. And again, this is the nice, easier case where we're just kind of looking at a line. Now, I could solve for t, right? Make this x equals 7 plus t, which means x minus 7 equals to t, and I could plug that t into there and get y equals 2 plus 2 times t, and t is x minus 7. And I could solve for y and get 2 plus 2x minus 14, and I could get y equals 2x minus 12. That's the equation of this line in function notation, meaning y as a function of x. But this just gives my a position, like where am I located at when I'm at a horizontal position of 5. Okay, I can plug in 5, and I can get negative 2. But this tells me almost nothing about the motion. This tells me so much more about what's going on. It tells me my horizontal position, my vertical position at any moment in time, my horizontal velocity and my vertical velocity at any moment in time. This is just a relationship. This is kind of like a map. Again, this is kind of old school function notation, and then we have a parametric, which does such a better job of describing motion in terms of time, velocities, and accelerations than this ever does. This doesn't tell us much. Okay, let's do another case. Let's look at circular motion. Okay, this one will get a little more difficult, but let's start here. And let's just kind of go in a circle. Okay, let's say we start here. And let's say this coordinate point was 5, 0. Okay, and that does correspond to a time equals 0, right? That's where we're starting. And let's say I tell you we go this direction around the circle. And let's say that the entire circle, to go all the way around, which would be the period, and I'm going to use a capital T for that, is 4 seconds long. Okay, so we start at this coordinate point, 5, 0. We're going to walk this direction around the circle, and it takes us 4 seconds to get all the way around. Again, that motion is fairly complex, but it's pretty easy to describe using parametric equations. So x is some function of time, y is some function of time, and when you think about this, okay, so if you can just break down your horizontal motion, really aren't you doing horizontal again? Forget vertical. Horizontal, aren't we going left, more left, back, and back? Horizontally, we're just bouncing back and forth, back and forth, back and forth. Well, and we want to start with an x value. So if you, hopefully you're thinking, oh, this might be a trig function. So a cosine curve looks like that, and a sine curve looks like that. And which one of these makes sense to use for our x value? Okay, look at our x value. It starts with a big x value and then goes to 0, negative x value, 0 x value, back to x value. Look what cosine does. It starts with an x value, starts with an x value, goes to the next value of 0, goes to the next value of 0, and then what happens to x? It becomes negative. Biggest negative. And then it goes back to 0 x value, and then it gets back to the start. And we completed one cycle of motion, one period. Okay? And so, well, what's the amplitude? Well, this, if you just use a normal cosine curve, you get an amplitude of 1. Well, we're going to go from 5 to 0 to negative 5. So it's going to make sense to use a 5 cosine. And then we have to wait on the period for a second. Okay, so let's talk about that. A normal trig function, if you just had to kind of graph a normal trig function, you would say something like x equals cosine of omega t. And again, that is an omega. It might look like a w, but it's an omega, and it describes the angular frequency of the cosine. You know, we might have put in like a cosine of 2t. Well, cosine of 2t will actually complete itself in that amount of time. It's going to go down fast, up, and boom. It's just shorter. Everything gets twice as fast. Well, if it gets twice as fast, it's going to also affect the period. The period is going to get cut in half if this is a 2. And so something that you hopefully learned in pre-calc says that the period, you can find it by just taking 2 pi divided by omega. And again, this is true for sines or cosines. They have the same period. I mean, they're pretty much the same function. They're just shifted. So in this case, if we want to do this complete cycle, right, one period of motion in 4 seconds, we want t to be 4. So if t is equal to 4, we can solve for omega. And again, solving for omega is finding the number that you multiply inside the trig function. And so when we solve for omega in this particular case, we're going to get an omega of pi over 2. So if we have an omega of pi over 2 here, that will force the trig function to have a period of 4 seconds. Okay, now let's go to the vertical motion. What happens to the vertical motion? It goes up, and it comes down, and then it goes down, and then back to 0. Well, look what the sine curve does. It starts at 0, it goes up, and then down, and then down, and then up. It's exactly what our vertical motion does here. We go up, and then down, just like this part, and then we go down, and then up, down, and then up. And so this is going to be a sine curve, so 5 sine, and we do want it to have the same period, so pi over 2t. And then the question is, are the negative signs correct? Well, we do want the x value to start at a positive 5, so this is positive, and then look at the direction. What do we want our y value to do right away? We want it to go up, meaning we want the y value to become positive, so we want a positive sign. If you wanted the motion to go clockwise, let's say, actually use purple. Let's say you wanted to go this way around the curve. Well, then we need a negative sine curve. Look what a negative sine curve does. It goes negative first and then positive. So we'd have to put a negative sign here. if we wanted this thing to go that way. Again, if you put a negative sign here, everything stays the same. Period stays the same, amplitude stays the same, still starts here, but it's going to go this direction with a negative sign. And again, look at the power of what I can do here. This is just a circle. Old school, what would this be? This would be silly. X squared plus y squared equals to 25. That's this exact same circle. This is kind of like old school function notation, even though this is in itself isn't even a function, but it's a curve. But the curve defined in terms of x and y is really fairly worthless in describing the motion. Look what all I get to describe when I have this. I get to choose a starting point, how fast it's going to go around in terms of the period, right? If I pick the period and I pick the curve, I'm also picking the speed at which it goes. I can take derivatives of this, just like I did over here, and find dx dt and dy dt. I can find the second derivative to describe the accelerations of these things. I can do all sorts of things, and again, this is what a parametric function does. It allows me, and I could even make this 3 dimensions. I can add a z of t as some function of time. And again, I'm really expanding what I'm allowed to do in describing the motion of an object, both its position, velocity, and acceleration, using some calculus stuff, by defining the function in terms of some parameter. In this case, we're going to use time. Okay, what if I wanted to do an ellipse? Well, an ellipse isn't really that much harder. All I have to do is stretch it. Okay, so let's do an ellipse this time. And let's do a vertical ellipse. So it kind of looks like that. Let's start here. That'll be fun. And let's go that direction. Let's have a period of 8 seconds. Let's have a starting position of 0, -6. And we'll say we also know that this position here is 2, 0. And let's describe that motion. Okay, so we want to describe the motion in terms of parametric. So we want x of t and y of t. All right, now where do we want to start? We want to start right here. Again, this is our starting point. I better label that t equals to 0. So when t equals to 0, we want the thing to have a -6y value. And again, cosine of 0, again, this is really what you're thinking about. Cosine of 0 is 1. Sine of 0 is 0. So whichever one you assign the cosine to, it's going to get the 1, or meaning it's going to have the starting value, and we want the y value. So how about a -6 cosine of some t? I don't know what the period is yet. We'll figure that out in a second. And then x value, we only want it to go back and forth between -2 and 2. So how about 2 sine? So this will make x start at 0 no matter what I put in here. If I put t equals to 0 in here, it'll make x 0, which is what we want at t equals 0, and it'll make y -6. Okay, so let's do the period. Same relationship is true. The period is 2 pi over omega, where omega is the number that's multiplied. And if we want the period to be 8, we're saying then we need omega to be pi over 4. So then we know that this is pi over 4t and pi over 4t, right? They're both functions of time. And I'm controlling the period right here, again by this same process. I'm going to make it start at a -6, because I picked cosine to be my y value. And now I got to think about whether this is a positive or a negative. And again, what do I want x to do? It starts here, and I want x to become negative. So this has to be negative. Think of the sine curve again. The sine curve looks like this, and we're going to use the negative sine curve to make sure that our particle gets a -x first, and then a positive x. Negative x first, and then positive x over there. And again, we started with the cosine curve, but we started with a negative cosine curve, because look at our y value. Instead of a positive cosine curve, we're going to use a negative cosine curve, because we want our y value to start negative, go to 0, start negative, and go to 0, and then have positive y value, and then go back to a negative y value. And again, look at that. Nice elliptical motion again. Lots of things travel in ellipses. You're traveling in the Earth right now, traveling around the ellipse, around the sun.